How high?
There should be 32.
Okay. So, tell me about this circuit. Are we above resonant frequency or below resonant frequency? And how do you know? We're above because the omega L wins over the 1 over omega C. The omega L is 3,000 ohms. The 1 over omega C is only 100 ohms. And so as a result, at the present time, we are at a frequency which is way higher than the resonance condition. That means we expect that our friend the inductor is going to get plenty of voltage. Our friend the resistor, not so much. Our friend the capacitor, not so much. Okay? That's what we expect because of our present condition. Everybody follow? Okay.
Wait, did you say
the inductor gets most of the voltage because it has the largest impedance. You look at the three impedances, the resistor is 600, the inductor is 3200, and the capacitor is 106. As a result, the inductor is going to get the most voltage, the resistor is going to get less than that, and the capacitor is going to get even less than that. Yeah, because it has the biggest impedance. Yeah.
I know it only gets left over, but when you look at that, did you see anything about the 600 on the resistor versus the 106, or that once you test the inductor?
We're going to get more on the resistor in this circuit than we are on the capacitor. Now, a real radio circuit. This would be very lousy in your car. Okay, because you see we're not at resonance, and 600 out of 3,000 is actually reasonably significant. What it would mean is that if you tuned in this circuit to one radio station, you'd hear all the others faintly, which would be no good. You want to hear all the others not at all. So in a real radio circuit, you actually shoot to get this resistor really, really small. So the only time it's significant is a perfect cancellation of these. Then you only listen to one radio station. As the resistor gets larger, then even if the inductor and capacitor don't cancel perfectly, it still may be getting something. And then that is called a resonant circuit with a core Q value, where Q stands for quality. Yeah, I know, it's not a unit list. Q is a little bit weird. But a high quality circuit will be when the resistance is very small, so that only a really close to perfect cancellation of L and C will give you a radio station. Now, in the olden days, if you made the circuit too high of a Q value, then the variations in the atmosphere inside that open-air capacitor would be such that you could never get it right. Okay, it's good! And then you walk away, and your body's influence on that capacitor is just tuning the radio. So then you walk towards it, and it gets louder, and then you keep going, it's soft again. No, back up! Raise your hand! Stand there! It's fading, it's fading! No, that's worse! That's better, okay! So if you made the Q value too large with a resistor that was too small, then in practical terms the radio would not be easily tuned because you couldn't hold the frequency. So the spacing that you presently have under radio stations goes back to the 1940s, or I guess it was earlier than that, when radios were first being developed, and the Q that was reasonable to hold a tuned circuit was decided to set the spacing so that you would design a not so great Q value and still not have another competing radio station so close that you could hear it also.
What's the formula for Q?
I forget. Okay, all set? So, we need one more thing. We need the phase.
Yeah, we didn't answer that.
Oh, we didn't get an answer.
Oh. 3,117.
The answer is 3217.
So the magnitude of Z total is 3217 ohms.
Yep.
And the phase of Z total 79?
Where'd you get that?
You take the inverse tangent of B over A. So B is 3726 minus 106. That thing divided by 600, inverse tangent is 79 degrees. So that's also an indication that the inductor is winning. Plus 90 is a total victory for the inductor. Minus 90 is a total victory for a capacitor. Plus 79, I'm pretty much there. Right, that's almost 80 degrees. This is an inductor that's in charge of this circuit. Yeah. Oh, these are going to always be very nice, and you won't have to add 180. The reason is you decide whether to add 180 in an inverse tangent by looking at whether the denominator is positive or negative. Since the denominator is R, it's always going to be positive. The numerator might be positive if the circuit is mostly inductive. Negative if the circuit is mostly capacitive, but the denominator is positive, period. So you won't be adding 180 to any of these inverse tangents to get these phases. Okay? Yes? Where did what? Plus 79. Plus 79 is the inverse tangent of this divided by that. So it's the calculation of the phi from the A and B. Phi is the inverse tangent of B divided by A. B is the difference, and A is just the R. Yes. Because when the phase is positive, the circuit is acting mostly like an inductor. So that means the voltage from the power supply will be happening before the current flows through the circuit. Okay, so far so good? Let's keep going. Yes. Reactance is what I would call magnitude of the impedance. Your book does not use complex numbers. Instead, they use this thing called phasor diagrams, where you draw vectors and play around with them, and then each vector has a magnitude. The magnitude of the vector is called the reactance. By using the term impedance, I don't need to refer to anything else, because the impedance knows its magnitude and knows its phase. And reactance, as a word, is the magnitude of an impedance. So the reactance of an inductor is omega L. The reactance of a capacitor is 1 over omega C, and the reactance of a resistor is R. And then we carry those terms around completely and entirely, but we have them coupled with the phase at all times so that we can whip through the calculations quickly. We get 2 done at once. Okay. Now, what do you think I'm going to calculate next?
Why wonder? I wonder what it is.
And is this equation in peak or RMS?
Yeah.
Yeah, it's in peak or RMS. So, what were we given in this problem? We're given peak. So in that case, I'm going to make my first calculation peak and my second calculation RMS. Okay? And the voltage on the circuit was our friend 10 volts with a phase of e to the I 0. And our impedance was 3217 ohms,
E to I.
E to the I,
79.
79 degrees, because it's almost all inductive at the present time, because the frequency is higher than the resonance point of this circuit, and that lets the inductor win over the resistor and the capacitor. So the magnitude is
10 over 3217.
which is what?
3.11 milliamps.
That's the peak. What's the phase?
Minus 79 degrees.
Yeah.
And what's the RMS?
2.2.
Repeat it.
2.2 milliamps.
So, this circuit has a current whose peak value is 3.11 milliamps, meaning that the RMS value of the current in this circuit is 2.2 milliamps, and this circuit has a current that is 79 degrees behind the phase of the power supply. Why is that? Because the circuit is mostly inductor, and inductors are what? Voltage first, then current. So as a result, the inductor overwhelming the properties of the circuit has caused the current to be backed up by 79 degrees as compared to when the power supply pushes, 79 degrees later, the current peaks. Okay? Because an inductor is voltage first. If we were in the regime where the capacitor were winning, then the phase of the current would be positive, because for capacitors, it's current first, then voltage. Everybody follow? Okay. So are all those phrases starting to hang together and kind of make sense, and you're anticipating the answers?
Starting.
Okay. Now I have three calculations. First one is voltage on the resistor.
Somehow I doubt that that's going to have through part T. Never know.
We'll get to the extra credit in a minute. Okay. So, what kind of a voltage were we given? Or actually, at this point, since we have the current as both a peak and an RMS current, we can use either one in our next calculation. There's nothing saying one's easier than the other, because we got them both. Which would you rather do as the next calculation, an RMS calculation or a peak calculation? Okay, I heard peak. In that case, the peak voltage on the peak current through the circuit is
3.11.
2.11 milliamps.
and the Z of the